Welcome everyone to this QEEE course on Introduction to Data Analytics. This is a 6-hour course, so we are going to try and cover as much as possible to give you a gentle introduction to the area of data analytics. As you know, data analytics is a vast field and there are many techniques and many ideas that are relevant here. To explain all of that in 6 hours, as you might imagine, is not possible. So we have a philosophy for the course, which is the following. The first 2 hours, we are going to keep it rather general, explain to you what this idea of data analytics is, what are the components in a data analytic exercise, and then to excite you into this field, I'm going to discuss case studies that we have done using data analytics for you to give a glimpse of the kind of potential that is there for this field. The second 2 hours of this course, what we will do is we will have fundamentals that are needed. Obviously, there's a lot of things that we need to teach, but we've kind of crystallized the most important ones that you need to learn and then try and teach you that for 2 hours. The last 2 hours, the first part, we will teach you 2 techniques in a little more detail for you to get an appreciation of how these techniques work, and then we will describe a case study which will be used as an assignment for you to do. So this is going to be the flow of the course. So what is data analytics? Data analytics is really the science of examining raw data and making useful conclusions out of it. And why are people very interested in data analytics now? They are quite interested in data analytics now because of abundance of data that is available now. Compared to about 20 years back, the amount of data that is available for people to work on has increased tremendously. And that is one of the main reasons why there is a lot of push in data analytics nowadays. And not only that, because of the proliferation of internet and social media, the types of data that you get have become varied. So you get tons of data of different types. And the question then is if you could use all of this data in a meaningful fashion to derive results that would otherwise have not been possible. So crisply, analysis of data is a process of us inspecting. Inspecting meaning take some variables, plot them and then see what happens. Cleaning, if there are mistakes in the data that are obvious, you need to clean them. You transform the data, you do some calculations with this data and then transform it to another form and basically model this data with the goal of discovering useful information which would suggest conclusions and support decision making in whatever you want to do. A simple decision making could be if you're looking for a restaurant to eat, what is the best restaurant that you can find around you to eat and so on. But if you are thinking about a chemical process, then a decision could be what temperature should I operate my equipment at and so on. So those are the kinds of things that we are interested in. There is also this notion of big data, and which is to be differentiated from data analytics. Data analytics basically pertains to algorithms that are derived to get meaningful information from data. Big data refers to the size of the data. Data analytics algorithms have been around for several years now, in fact couple of decades or more, the type of algorithms that we are talking about. However, they used to work with very little data because data was not as available then as it is now. However, as I mentioned before, because of the availability of lots of data, big data refers to data that is available in very large quantity. And one of the excitements of data analytics is now that data is available in large quantities, is it possible to use this large quantity of data to do things better than what we were doing before. So how big is the big data? There are certain statistics that we give here. For example, if you think of every mobile phone as a device that is collecting data and then sending data to some storage, then you can see that there are about 4.6 billion mobile phones in use and so on. So this gives you an idea of the kind of data that is being collected which can be used and leveraged for various purposes. There are also estimates of this value of big data. Just if you look at potential annual value for US healthcare alone, it is estimated to be about $300 billion and so on. and similar numbers you can see in Europe and other places. The other interesting thing that comes out of this is that with this data being available and newer algorithms being developed, the requirement of data scientists who can work in this area is also increasing, and by some estimates there are going to be hundreds of thousands of jobs that are going to be created in this field, and that is also one other reason for excitement in data analytics. So to give you some notion of what people talk about in big data, I am going to talk about what are called the 3 V's to give you an idea of different dimensions in which one looks at data. The original 3 V's of big data refer to 3 things which are called volume, velocity and variety. Volume, as you might imagine, is just the quantity of data that is being generated. Velocity refers to the rate at which data is being generated. Do you have tons of data being generated in a second or a minute? So that's the velocity that we are talking about. And variety is the types of data that is being generated. So is it numeric data, it is symbolic data, is it text data, or is it pictures, audio, video, and so on. Okay. So these are 3 important aspects of big data. If you have volume but do not have velocity, then there are certain things that you can do with the data. But if the data has very high volume, very high velocity and very high variety, then the data analytics algorithms will be challenged to use this data to come up with meaningful conclusions. Of course, IBM added one more V later, which is veracity. Veracity in common English means how true something is. So you might talk about a lot of data coming in with volume, velocity, variety, but how reliable is this data is what veracity looks at. Now, if you decide that the data is not very reliable, then you have to really correspondingly look at your algorithms and then see how you would make sense out of data that might not be intrinsically correct. And as we mentioned before, the sources of data could be machine generated data, human generated data, and so on. So here are different information sources that Gartner puts out. It could be social data, it could be documents, it could be transactional data where you go and buy something and pay with a credit card. It could be IT, OT data, image, audio, video, mobile, and things that you are searching also becomes part of data that can be used in analytics. Now, while we have lots of this data, you have to remember just collecting data does not mean you discover something about something, right? So you could have tons of data that you have collected, but you still need to be able to make some sense out of the data. Data should lead to value propositions. And this art of converting data into knowledge is called data science. And data science basically has 3 components, 3 large components I would say. One is the domain knowledge. What is the type of domain that you are working with, and how do you apply a particular data analytic algorithm for the domain that you are working with. Lots of data science algorithms take advantage of statistical principles and mathematical principles. So one has to be strong in these, and one need to have good coding ability to be able to work with data science algorithms. So these are the essentials of data science. Now, in summary, as we talked about till now, data analytics has 2 components, data and analytics. Data refers to the kind of data that you have in terms of volume, variety, velocity, veracity. And there are lots of things that one needs to do in terms of how do you collect this data. If you have a mobile phone and you are doing something, how do you bring that data to a particular system? If it's an industrial facility and there are the sensors which are measuring things and actuators which are actuating various important variables, how do you get that data into your system? So that is collection, and once you collect, how do you make sure all of this data makes sense, remove outliers, fill in data that is missing, what is collectively called as curating this data so that it becomes a complete set that is usable. And how do you manage this data? If you have tons of data, do you put it in one place, do you spread it around, how do you query from this data, and so on. So there are lots of computer science kind of work that one needs in data analytics, and that is the data part. The other part is analytics, which is actually once you have this data, how do you come up with algorithms that make sense out of this data. Here is where we talk about machine learning techniques, statistical methods and so on. So in some sense, when a good data analytics algorithm works with large amount of data to provide meaningful conclusions, one has to really think about whether the data is sufficient, whether data is of sufficient quality, do I have methods that are sufficient to solve the problem that I am interested in, and are these methods robust and method quality to finally do what I want to do. So this is in summary and as an overall view of what data analytics is, what the data part of data analytics means, and what the analytics part of the data analytics means. The first part of data management and so on has several issues that one need to address, such as how do you design the database, how do you query from the database, how do you curate the data, and here how do you efficiently use the data so that the algorithms can look at a very large amount of data and find what is of interest, where you have concepts such as MapReduce and so on. We are not going to cover those in this course. What we are interested in is actually teaching the data analysis part of it. Assuming data is there and you have certain things that you want to do, how do you go about doing it is what we are interested in this course. Now, as I said before, this is a vast field. You can have 2-3 semesters course running for this field itself. So in a 6-hour program, what we want to do is give you at least some basic ideas that you can take away and then find avenues for further study. So we have structured this course in this manner. In this first 2-hour lecture, instead of directly jumping into the math behind this, what we are going to do is we are going to show you why this is important through various case studies, just to show that these analytic techniques are cross-cutting several disciplines. I am going to take one medical imaging case study, one financial analysis case study, one smart city case study, and an engineering analytics case study, so that we cover a broad spectrum of interest of the audience for this course. These case studies have lots of detail that go behind each of these. Since we are going to spend about 15 to 20 minutes on each of these case studies, it is going to be described at a higher level. What we would like you to do is basically understand the case study, and what is derived from the case study from a data analytics viewpoint is what we are interested in imparting. The finer details of the algorithms and so on, you would require a lot more background to understand. Okay, so in some sense we might do a flashback and then say, you know, how did we get here from where we were about 20-25 years back. If you were to ask me, I would say ultimately wherever we are, what we want to get to is what I am going to call as this information rich situation, right. So what we want to know is whether we have enough quality good information about the system that we are trying to explore and understand and solve problems for. About 30 years back, there were not this proliferation of sensors, there were not these many sources of data. So what people used to do was take a system and then model it to the highest level of detail. So what I am going to call as over model, and this was based on physics and chemistry and math principles. And the notion was that if the underlying principles were right, I would be able to model my system very well, understand it, and then be able to do whatever I want. However, the standard problem was you could write very detailed model for a particular process, but there will be several parameters that will be part of the model, and for you to be able to estimate those parameters for meaningful analysis, you needed enough data. So About 25 years back, the problem was really data sufficiency. You could really use lots of your domain knowledge to write very detailed models, but ultimately one was stymied by the fact that you might not have enough data to estimate all your parameters to a reasonable extent. Move forward to now, what has happened is that because of this tons of data, suddenly you have data about everything and anything. Now the question is, do I need a model even, right? Because I already have lots of data. All the information that I need is there in the data. Can I do something? Like the problem of data sufficiency when you had not enough data. When you have too much data, there is this inclination to overanalyze. So it might happen that your algorithms are doing garbage in, garbage out, which is not a good situation. So what we have gone is, we have gone from a data poor situation to a data rich situation. Nonetheless, our focus has always been on becoming information rich. Now the question is, can we do smart analytics with data so that we get to this information rich situation. Just for people to understand what are the common activities in a data science project, even if you know lots of algorithms, there are certain basic steps that are done in any data analytics project. And what I am going to do is I am going to use a cartoon, a very simple example to kind of explain what are the different activities in a data science project. So if you think of a data science project as putting together a jigsaw puzzle, so you have various pieces of data, you have various pieces of knowledge, and there are many methods out there that you could use. Now the question is, how do I put all of these pieces together so that I get a solution which is a completed jigsaw puzzle that is useful from whatever I am trying to do. So in general, if you look at the left hand side of this slide, there are many pieces. So these pieces could represent the several types of data that is available. You might have data which is video, audio, actual process measurements and so on. And you also know that if you go to any data analytics package, there are several tools that are available, right? So the data is available, tools are available. Are we ready to solve the problem? Can I solve the problem? It turns out that in most data analytics problems, as we see it, the most difficult first step is to define what we want to achieve. Most of the time, there is this tendency that there's a lot of data and I can use this data to do something meaningful. But really, what does that something meaningful mean? And it looks like it's a very simple question, but it turns out that this is a very difficult question to answer in general. If you get this question right and the answer to this question right, then the other parts of data analytics become simpler. So this could translate in terms of this cartoon to what is a puzzle going to look like once assembled? What is a solution? If I had a solution in hand, how would it look like? What can I do with that solution is a question that you ask. If you were given this puzzle, the very first thing you would do is you would remove the unwanted pieces that are there in the puzzle and focus only on the important ones or the relevant ones. So from a data analytics viewpoint, what we need to do is we need to focus on the right data, we need to focus on the right methods. That basically means you discard redundant information and discard methods which are either too complicated or not relevant for the problem at hand. So from the previous slide where I had several pieces, let's assume that we have thrown several of those pieces and then you have this remaining. It's still not ready to be assembled. Once you figure out what data is important and what techniques you are going to use, in general, any data that one uses will not always be perfect. There will always be errors in the data. Data might not be in the form that you are interested in. So basically the data needs fixing, and also in some cases there will be a typical method that you could use, but the method might not give you exactly what you are looking for. So you might want something else which is slightly different. The basic idea of the method can be used, but you need to tweak the method a little bit. So those are two things that you do. This is like actually fixing some of the pieces which are not proper. So data needs to be clean. And this is a very interesting aspect. While we talk about data and then I will do lots of things with data, in many cases, at least in my personal experience, this data cleaning requires that you have some domain knowledge about what you are trying to solve. For example, if you know the data is let us say temperature, then you would say, look, negative temperatures are not meaningful, right. However, if you are working with money and then you are going to say negative as money you owe and positive as money you gain, then it might be okay to use negative and positive for the data variable. So it is important to have some knowledge about the domain that you are working with, right. So you cannot, so if the temperature turns out to be a number which is 10,000, then you would really worry about it. Does it make any sense? So domain knowledge becomes an important aspect of data cleaning. And like I said before, existing methods might have to be tweaked for you to be able to do data analytics. Once you do all of this and finally put this together, you see this beautiful elephant, which was your original puzzle. And if you didn't do those final steps before, you would not be able to get this elephant as your final solution. Do we want to break and ask them if they have any questions? Okay, do you guys have any questions till now? Can I, you can post. I'll just wait for a minute. If you have any questions, I will answer. Otherwise, I will continue with the first example. What I will do is, after the first example, I'll again break and ask them if they have questions. And if they don't have, I'll go to the next example and so on. So looks like there are no questions. So I will proceed with the first case study. I just want to mention before I go through these case studies, these are case studies that we have worked on in various situations, some of them here at IIT, some of them in other companies and so on. What I am showing here are the key ideas in these case studies, and then kind of show you the variety of case studies that what one could work with. So the first case study that I am going to talk about is data analytics of images for medical diagnosis. So here, as we all know, if we do a blood test, we can get the hemoglobin levels in the blood, which is actually an invasive kind of test where someone has to prick, get the blood from the patient and do the hemoglobin level. One interesting question one might ask is that if there are other non-invasive tests where no blood is drawn, where you are still able to identify your hemoglobin level. So is it possible to find out the hemoglobin level from, for example, images of eye, right? Now you might wonder, why is this an important problem? This is an interesting problem, particularly for veterinary applications, where if you have a cattle farm and you have lots of cattle, you want to test their hemoglobin level, it's going to be difficult to shepherd them to do this blood test and then do your hemoglobin level. So is it possible to just take a picture of the eye, the conjunctive area in the eye, and see whether you can identify the hemoglobin level? So that is the problem description. So for example, here are two pictures of cattle's eye, and in one, depending on the shade, you have hemoglobin level. So this is one with a hemoglobin level of 9.9, another one with a hemoglobin level of 7.8. Yeah, we were here. So as I was mentioning, this is hemoglobin level 9.9, and the next picture with that color represents hemoglobin level of 7.8. So the color characteristics can be related to hemoglobin concentration, is the hypothesis. Now this is an hypothesis. So in a typical data analytics project, usually you make an hypothesis like this, and you need to have test data to validate your hypothesis. So in this case, what it would mean is you should have actually pictures where a blood test was done and the direct hemoglobin level was also identified, so that you predict the hemoglobin level just based on the color of the eye and then match it with whatever was a lab result. And if the match is good, then you know that your algorithm is working and your hypothesis might be right. Now when we talk about color, so this is in this case represented by relative shades of red, green and blue. So when you have an image and you say I am going to use this analytic algorithm, so most of the analysis algorithms work with numeric data. So in this case, what you could do is you could capture the information about this red, green and blue for each pixel in the image, and then use some notion of a mean or a median value to convert the image to numbers. So what you do is you take an image, you convert that to numbers in terms of RGB, which would be mean or average values, and then you try to correlate these outputs to the final output that you are interested in, which is the hemoglobin level. So for example, if you take particular sample, this would represent some image from some cattle. So red 164, G82, B92, and then there was also a test that was done and the hemoglobin level was identified to be 9.9, right. Similarly, there is another sample where you have the hemoglobin level which is identified at 7.8 and so on. What you could do, remember I talked about transforming data. So if this were your original data that you had, below that we show a case where the same samples exist. You have A613, B565. You could use whatever data you have, but you could also derive other pieces of information from this data and use those also as inputs to be able to identify what the hemoglobin level is. This is what we mean when we say we can also transform the data to identify the final output. So one simple technique that one could use is what is called linear regression, where basically you try to correlate or represent the output as a function of the inputs, which are the RGB values. So you might write a linear regression expression which says hemoglobin level is equal to A0 plus A1 times R plus A2 times G plus A3 times B, right. Now if you were able to identify the values for A0, A1, A2, A3 from the data that you have, then whenever there is a new picture that comes to you, what you could do is you could use the same process to get the average R, average G, average B, and then plug those values into this equation once you know A0, A1, A2, A3, and once you do that computation you will get the hemoglobin level. So that is how a simple linear regression works. Now how do you get the values for A0, A1, A2, A3? What you do is you have several samples where you know the values for R, G and B and hemoglobin level also. So you use the data from all of those samples in a collective fashion using what is called a linear regression technique to be able to identify the values for A0, A1, A2, A3. Okay. So this is one way of doing it. Now there are more interesting things that one could do. When we are doing a linear regression like this, since we have a term for each A0 which is a constant, R, G and B, what we are basically assuming is all of these variables R, G and B independently have information that can be used in the calculation of the hemoglobin level. But in some cases it might be possible that some of the input variables themselves are correlated. In other words, if you give me R and G, if I were able to predict B from R and G itself, then having a separate term for B is not necessary, because that information is already captured by R and G, and by adjusting A1 and A2 and A0 we can somehow bring that information to bear in the problem. So there is a technique called principal component regression, where you could identify whether the input variables themselves are correlated, and reduce the number of input variables that you use to predict your output. So that is another technique that you could do. And notice here I am describing all of these techniques at a high level where you can understand the basic idea behind it, but the theory and how do you do principal component regression and so on are left to you after this course is over and you do more courses to go and look at and then see how these are done mathematically. Nonetheless, in the next 2 hours after today, this Friday, we will give you some of the tools in terms of linear algebra and statistics that you would need to be able to start reading how these techniques work and start making some sense out of how these techniques operate. Now, the thing that you notice here is if you look at the first equation where hemoglobin is A0 plus A1R plus A2G plus A3B, you notice that the equation is linear. They are just additive terms and each of these input variables are used as they are, R, G and B and so on. However, the real truth might be that the hemoglobin is not linearly related to R, G and B, but it might be non-linearly related to R, G and B. So is it possible to build those non-linear models? Yes, it is possible. There is a technique called kernel principal component regression, which can be used to get nonlinear combinations of R, G and B from data itself and do this prediction so that you do the prediction for the hemoglobin level at a much better accuracy. So typically when you set up a data analytics problem, as we talked about before, you clean the data, you modify the data. Here modification basically means that I take the images and I modify the images to numerical values for R, G and B. Once I modify that, then I set up the actual data analytics problem, which is based on my hypothesis that I can predict hemoglobin levels from the picture itself. So that hypothesis has translated from I can build a model between hemoglobin and the picture to hemoglobin and R, G and B. So that is the sequence in which we have come up here. And once you say, okay, I can fit a model for hemoglobin in terms of R, G and B, then the question that you could ask is what type of model? The simplest model turns out to be linear, but you could question that as you go through the process. The simple model does not give you the desired result, then you could go on for a nonlinear model and so on. So this is the sequence in which you do this data analytics process. There is another interesting thing that you need to do, which is if you let's say have 100 samples of data, when you build a model, typically what you would do is you would not use all the 100 samples to build a model, because once you build a model you will then be left with nothing to test your model with. So typically the simplest thing that you could do is if you have 100 samples, what do we mean by 100 samples? There are 100 pictures and the corresponding hemoglobin levels. If you have 100 such samples, you might randomly pick 80 pictures out of this and build a model with these 80 pictures and then use the remaining 20 pictures to be able to see whether the model that you have built, when tested on data that it has not seen before, does it still do a good job, right? So you could split it 80, 20, 70, 30 and so on. It all depends on how much data you have. Supposing you have only 10 data points, 70-30 might not be a good idea, right? So you might want to do something else. Now if you have smaller data sets like that, there is another technique that you use to validate your model, which is what is called as leave one out cross validation. What you do here is if you have let's say 10 data points, you leave one out and then the remaining 9 you fit a model and then predict for the one that you left out. There will be an error. Similarly, leave some other 9 out and then predict the error for the remaining one that is left out. So you can repeat this, for example, if you have 10 data points 10 times, right, because you can leave any one of the 10 samples out, and then once you have this error, you look at that overall error and then see that is your testing error. So this is a simple technique that you could use if you have small data sets. If you have large data sets, you could simply break them into two, but you would do this randomly, the breaking, because you do not want to systematically bias your sample based on any preconceived notions that one might have. So here are the kinds of results that we got with this example. The first linear regression that we talked about, we got about 21% error in predicting, which basically means if the hemoglobin level is 8, you might predict 6 or 10, right, which might not be very good in terms of a performance. So here we also said, look, okay, it might be because this is a linear model that we have used. Maybe if we reduce the dimensions or use a non-linear model, our predictions will improve. So when we use a non-linear model, which we are showing here, KPCR, the error reduced but not by much. So it was still 20.1%. So really at this point is where data analytics requires good data scientists. So till now, if you were to do this linear regression, you do not have to write any code at all. If you want to do KPCR, you do not have to write a code. All of that exists. All you're going to do is simply use that code to do these predictions. But once you do the basic analytics and then you have some results, and then now it's a question of analyzing the results and doing diagnosis with these results and trying to see what went wrong and how do I improve this, is where a real data analytics person's skill comes into picture. So in this case what we said was, look, linear and non-linear didn't seem to matter, so there must be some other reason for this poor performance. In general, there might be two reasons that you might have. One is that there are more variables that affect the hemoglobin level which have not been captured by our data set. So we have a picture from which we have taken RGB, but that might not be enough for prediction in this case. So are there other variables that might be important, is one question that we might want to answer. Of course, you would also worry about how good this data is itself and so on. So we did more analysis with this, and then we realized that when you have a same picture but a different lighting, you will get different results. So for example, I am sitting here in front of you, in front of this camera, and I have lots of lights focusing on me, so you see a particular picture. If the technician were to simply put one light off, and you will see I am not changed, I am the same person, but the picture you will see will become different. So it is important to understand what lighting was used. So if we were to capture a picture with one of these bright lights off and all of the lights on, then there is going to be a difference, right? So somehow you need some standard for what the lighting effect is, so that you can do better performance. So here, for example, once we started getting data, in addition to the picture itself, you also get a picture of a light standard. So you know that is a standard at a certain lighting condition. So wherever you take a picture of the eye, you also keep this, and depending on whether you get the same image back for the standard or different image, you can figure out what the lighting changes and somehow use that information to kind of normalize for different lightings and see whether your results get better. So this is called a photographic standard. The point of this first introduction course and then trying to explain these case studies is the following. So when we talk about just teaching techniques, you could take these techniques, understand them, but that does not finish data analytics. There is lot more intelligence, lot more thinking, lot more structure that you need to bring in for you to be a good data analytics researcher or a practitioner, and that is what we are trying to demonstrate here. So how did we remove the light effect? So what we did was, since we are getting RGB values, we also use the standards that we get. So with every picture, you don't only get RGB of the eye, we also get the RGB of the standard. Since we were interested in normalizing this, what we did was, we said, okay, the hemoglobin level will be a function of the normalized RGB, where the normalization is done with respect to the standard, right? So depending on the lighting, the standard will vary. For example, if standard lighting, if you keep RS, GS, BS as 1, if it's poor lighting, it will go in one direction. If it's brighter lighting, it will go in another direction, and so on. And once we did that, we got much better results from what we had before. So this is a very interesting example of analytics because computer vision and analytics of computer vision is a big field in data analytics. There are lots of applications that people are thinking about. You could use computer vision based analytic chemistry, which is called CVAC. A large number of people working in this area. People are talking about using your smartphones and attach microscopes so that you can do low cost imaging, which could be very useful for point of care diagnostics and so on. For example, if you have a blood sample, can you use a smartphone with a microscope attachment to image it and then do diagnostics and so on. So whenever you want to do any of these, image acquisition and processing are important steps. We demonstrated that in the previous example. If you didn't use the photographic standard, there was a problem with the results. And this kind of computer vision in medical diagnostics has many other applications also. Anomaly detection, recommending preventive solutions for diseases and so on. So there are lots of interesting applications that one can think of. So this is the first of the 4 case studies that we are going to discuss. So I will pause now, and if you have any questions, I will be happy to answer them. Okay, so if there are no questions, I will go on to the next case study. So this is interesting work that we did with the company. So this is very different from the previous case study, and it has been deliberately chosen this way so that you get a flavor for the various types of applications that are out there. So this is the use of data analytics in stock markets. There are several things that are being done here. This is a very preliminary level, very simple example that we are showing here for you to kind of understand. Typically, when you have stocks and then you take a ratio of some stocks which you expect to move together. For example, if there are 2 companies which make cool drinks, and you would expect in general, barring crazy things that happen, that the stock prices of these 2 will go together. Then what you could do is you could take a ratio of a pair of these stocks, and then you plot that with respect to time in days. And if for example this curve keeps going up, then that basically means is that the stock whose value you had kept in the numerator is increasing in value, or the stock in the denominator is decreasing value, or both the value of the stock in the numerator and the stock in the numerator is increasing and the stock in the denominator is decreasing. In other words, they are moving away from each other. And if this curve keeps going down, then that basically means that again the stocks are separating from each other, but now in favor of the stock in the denominator. So if it's moving up, it's separating in favor of stock in the numerator, and if it's moving down, it's separating in favor of the stock in the denominator. Now this notion of mean reversion is the following, where since these are very commensurate, that basically means that because they are in the same sector, they are very similar in profile and so on, whatever is the original mean of this ratio, barring very strange happenings, you would expect that mean to be the same. So what this basically means is the following. So if let's assume, just for the sake of argument, if the mean is somewhere around here, then what you would expect is, if this goes up, which basically says stock 1 is improving, it cannot keep going up because they have this notion that these stocks are commensurate. So at some point this has to revert back to its mean. So that's a mean reversion, and if it does this, at some point it has to revert back to its mean, and so on. You could do some strategy of buying and selling stocks based on this notion of mean reversion. In other words, if the ratio keeps going up, since the hypothesis is at some point the ratio is going to start coming down. So what you are interested in is in predicting when this is going to happen, because this is a good place to buy or sell. And similarly, you would also want to be, you will be interested in predicting this, so that that's a good place to buy or sell. So you know that you're not going to get any better, so you take some decisions at that point, because you know the trend is going to change. So one of the interesting questions is, if I have this data, can I figure out when this mean reversion will occur? So here is an example of the mean reversion occurring. So for example, if you take this plot, this is the stock value which is here and which started going up, and at this point it started coming down, and then it cut across the mean, and then it went up again, and then this keeps happening. Right. So these are basically what we call as the mean reversion points in this graph. Now there are also cases where, while this might turn down, it doesn't turn down all the way but goes up again. So for example, if you see here, it turns up and then without touching the mean it goes back again. So the question is, would it be possible for one to predict what points are true mean reversion points and what points are not really true mean reversion points? In other words, if it starts turning at the top, would it cross the mean, go down and come back? Or for example, it will do something like this. So you start here, turn, and then but you go back like this. So you want to avoid predicting mean reversions at these points, because you're going to get back better value later. So is there some way of doing this? Is an interesting problem. So what we did was, we kind of developed an algorithm for conceptualizing and automated fashion finding out what could be mean reversion. Remember, these algorithms are based on some hypothesis, and typically in problems like these are heuristic algorithms which you demonstrate works with lots of back validation. You take the algorithm, look at data from before, and then try and see when you apply the algorithm, were you able to get the correct result, and so on. And in general, these algorithms will work for a while. You would look at this algorithm for let's say a few months, and then see how well it works. But in general, after a while, these need to be tuned or replaced, because the markets are very dynamic and you cannot have static algorithms working all the time. In any case, given these caveats, what we wanted to do was develop an algorithm with some self-learning capabilities and robustness to trends in market. So the question is, simply put, whenever this curve turns, can we find out whether it's a real turn or it's a turn for a short bit and it's going to come back again. Now if you are able to predict this, then you can really increase profit and minimize what is called mark to market losses. So what we did, the input, so anytime you have an algorithm that you're working with, the typical questions that one asks are, what are the inputs to the algorithm, and what are the outputs that you expect out of this algorithm. So in this case, the inputs are stock data from across different sectors for the past 5 years, and the challenge was to really come up with an algorithm which will do a better prediction of mean reversion. So there are standard techniques for mean reversion prediction that already exist. Now those become your benchmark, and you want to see whether you can come up with techniques which would do this mean reversion better. What we did was, so like I said before, these techniques, you use some characteristic of the data that you have been observing for the past few years, and then try and see whether that can be used in a prediction. In this case, we came up with some measure called volatility, which was used to see whether a mean reversion is going to be truly a mean reversion or not. So the volatility index was an index that we developed, which would be a metric to identify mean reversions that are true, which means that these are profitable mean reversion. So the way that we looked at this was, there is a band of values that one comes up with based on certain calculations that one does. So in general, you want to think of this as a prediction of what would be the band of mean value. So for example, if you take the green line here and here, it kind of makes an envelope for your moving average of the data. So if you take a moving average of your stock value, then this band tells you this moving average will be within this range. Kind of think of this as an uncertainty. And what we noticed was this uncertainty band. When you looked at data, the behavior of mean in reversion was different when this band was narrow as opposed to when the band was not narrow. So basically what we did was we not only used at the stock data, we also constructed this mean moving average and then looked at this band value and then figured out based on index which measures how apart these band values are to see whether even though the original stock trade numbers are curving back, is this truly a mean reversion or not, and depending on what region of the data you are, whether you are here, here or here and so on. So we had some algorithms are trying to predict what will happen with mean reversion. Now when you notice the previous slide, you will again notice that this is not a standard algorithm, this is not something that people do in a standard fashion. But the reason why I put up this case study, the simple case study, was to illustrate the idea that all of analytics looks at characteristics of data and then tries to see if one could take advantage of these characteristics to make better predictions. So to be able to do that, the characteristics that you are identifying should have some relevance, and these are heuristic characteristics. So you cannot really mathematically prove that they have relevance. So the way you prove is the following. So you look at these characteristics that you have identified and then you come up with an algorithm. You take this algorithm, let's say in the last 5 years you had this data and you exactly knew where actual mean reversions took place and where it didn't, and then run your algorithm, look for the same characteristics and then try and predict for the past data how much mean reversion will occur or not. And since you know the truth of what happened, you compare those two and then see whether your approach worked well or not. So what I am trying to emphasize here is in many of these analytic algorithms, you could look at some of these heuristic factors or some of these local characteristics of data that could help you in predicting some things better, but it is important and it is incumbent on the data scientists to really look at how to validate this before applying it. So in this case the validation was quite simple because we could look at the data for the past 5 years and then run the algorithm, and then if this algorithm did much better than standard algorithms, then you said okay, there is some merit to this algorithm, so I will use this. So this gives you an idea of how you start looking at different problems and then look at analysis differently. So in the previous problem where we had very clear hypothesis, we said color is related to hemoglobin levels. We did our first model, we did the linear model, didn't find it to be good. We improved it to nonlinear, we didn't find it to be good. Then we really looked at a very domain specific knowledge where we said okay, the picture that you take really depends on what lighting you have, so there needs to be a standard. So that is a very physical insight. And then once you have the standard, how do you include that into your algorithm? There are many ways of doing it. We did it using normalization. So that is one process by which we solve that analytics problem. In this case here, there are already several algorithms that exist for predicting mean reversion. So we wanted to look at very specific stocks and whether there are certain peculiarities and characteristics of those stocks locally in time that one could take advantage of in doing predictions. So pure observation, plotting, doing calculations, we were able to look at this phenomena of funnel where depending on how separated these upper and lower bounds are, we found that the true mean reversions changed. So that heuristic idea was used to develop an algorithm, but once that idea was used to develop an algorithm, one had to really go back and test the algorithm. So what we did was we took past data where we knew the truth of mean reversion, applied our algorithm, checked it, and then we are able to say, okay, this is working all right, so you deploy it. But what happens in these cases is that it will work well for a while, and after a while it will start performing poorly. So you need to have some notion of self-learning, or you have to change the algorithm and so on. So that is the second case study, and as I told you before, these are very different case studies from my experience, that one can show the promise of data analytics and how many different fields in which you can use this. And that's how these case studies have been picked up. I'm going to again pause for a couple of minutes, wait for questions. If there are questions, I'll answer. Otherwise, I'll go on to the next case study, which is data analytics in smart city planning. Okay, I assume that there are no questions, so I'll continue. The next example, it's a very interesting example. It's a real attempt at data analytics, and the way we got to that this problem is an interesting it's an interesting experience. But in any case, one of the things that the government has been talking about for a long time now, both in Tamil Nadu and other parts of the country, is to fit the meters that one uses in auto rickshaws or cabs and so on with GPS data. GPS data basically gives you the location of that device. So if you put this device in auto rickshaws and cabs, then you could basically get information about their locations in real time, both spatially and temporally. What I mean by spatially and temporally is where are they and at what times are they. While effort is still going on, it's not fully done yet. In other words, if you go to Chennai, you do not have these auto rickshaws with these meters where GPS reading is being streamed to some central location and so on. However, looking at the future, and let's say we had data like this, one might ask, if you have, let's say, 150,000 auto rickshaws in Chennai, and imagine that these auto rickshaws are sending their GPS location information even, let's say, every minute, then immediately you see the kind of data that you're going to get, right? Because every hour you're going to get 60 minutes, and in a day there are 24 hours, and then you have this 150,000 autos which is trying to stream this data in. So slowly this starts looking like a big data problem when you look at all the auto rickshaws around India and so on. So other than safety and an ability to figure out how much fare should the consumer pay for the ride, can one do something else with this GPS data now that we are talking about big data and data analytics algorithms and so on? It's just as amazing that all through the world, all around the world, that this kind of data is being looked at. For example, here are 3 news items I have put together in this slide. GPS data on Beijing cabs reveals the cause of traffic jams. So basically, you look at how these autos are moving, what locations they are moving, and once you get this position at a reasonable rate of data, if you start getting this position data, let's say in seconds, then you could also use this data to identify not only position but also velocity, and then you start getting a picture of how the traffic is moving and why was it moving freely at some time and then suddenly they started crawling, or why are all these auto rickshaws jammed in one place, cabs jammed in one place and so on. So interestingly, people have shown that you could use this kind of GPS data on cabs to reveal the cause of traffic jams. Again, another news item which says cell phone GPS data suggests new strategy for alleviating traffic tie-up. So here For example, if you start getting data from all these vehicles, and as they are moving, you look at patterns from before where you said, okay, if there is this map of all of these vehicles, and I know when I had this map, after a while I had this traffic jam. So is it possible to keep looking out for a map of all the vehicles, and then when it becomes like a map which was seen before which led to traffic jam, can you kind of divert this traffic, change the map so that traffic tie-ups don't occur? And if you have this problem solved, all of us, of course, I do not face this problem because I am within the campus and I go to work in about 2 minutes. But I am sure many of the people who are commuting to go to work spend half an hour, 45 minutes, an hour sitting through traffic in the morning and evening. If it just could remove this problem, you can improve human productivity, you could improve the utilization of fuel and so on. So there are many things that one can do. When you have data like this, what are the things that you could do? So this is a fascinating thing because as young engineers, I would like you to think about all the types of data that one could, and from in this case from the same kind of data, how much value that one can get. For example, just leveraging the GPS data alone, you could develop what are called traffic heat maps, where you see that if it's very red, you know traffic is very high in these regions and so on. You could develop what are called waiting time heat maps, which basically says if you go on a road, how likely is it, or how much time would you take for you to go from a point to another point on an average. So that's something that you can develop. And how long are you going to wait in different signals is another thing you can develop. So for example, if you have many signals in the city and you know that the wait times are very high for certain signals, you could actually try different things to see how to remove this. So for example, is there a correlation between how long a signal is either red or green to the waiting time, right? So that's another thing to study and so on. So if you can coordinate all the signals in the city so that the waiting time comes down, that's another use of GPS data. You could schedule police if there is a lot of traffic in a particular location and you have this data real time, then you could deploy more police to those regions and less police to other regions. You could figure out times of day when traffic is less in different parts of the city, and if one were constructing roads and so on, one could schedule the construction of the road so that there is minimum disruption to traffic. And because you know the GPS location all the time, you can do automated toll collection. You can get rid of the toll booths because whenever you cross this, it's known that you crossed that toll, so you can directly be billed and so on. So what I'm trying to say here is just a simple GPS data, if you have enough of that, from many players. So here it's a very interesting data analytics problem where you get the same type of data, but the same type of data you get from multiple agents. And if you think of each of these auto rickshaws and cabs as each one of them as an agent, then you have multiple agents from whom you are getting the same type of data. And once you start getting this same type of data from multiple agents, imagine the number of things that you can do. If you are getting the same data from only one auto rickshaw, you can do pretty much nothing. But once you collectively get the same data from multiple agents, just one type of data could be used in so many different applications. It's an interesting thing to think about, the power of data and how one could think of various ways of using this data to do very interesting analytics problems. So you can do policy making in terms of signal scheduling, traffic management. You can directly catch traffic violations. An interesting thing, if you have an auto rickshaw and you have the meter, and if you're getting data at good velocity that we talked about at the beginning, then you could start developing velocities of this auto speed, and if the vehicle goes over speed limit, you can automatically impose a fine on the vehicle and so on. So it's a very interesting problem where you have data from different agents, the same type of data, there is no variety here, but if you had enough volume and velocity, you could really do lots of interesting analytics work with this. What we also realized was that if you could do so much with just GPS data, if you were to think of these auto rickshaws and cabs and the meters that are fitted on those as agents which are collecting data, and if you are able to get, let's say, disparate data from these agents, why only GPS data, why not video data, why not audio, noise data, pollution data and so on, then one could see the number of things that one could do with this kind of data, and it could have a direct impact on quality of life is something that we realized. So are there others doing similar things all around the world? It's very interesting that in the West the same kinds of things are being done. People are spending lots of money to find noise maps of London, millions of dollars spent in trying to find noise map for Long Beach, California. So noise map basically means just like your heat map, if you have a map and then say these are noisy regions of the city and these are less noisy regions of the city, and you don't only give this spatially but also temporally. What we mean is you might have a region of the city which is non-noisy during day but could be noisy during night and so on. So if you get this kind of information, you can use this in many applications. Similarly, pollution, all of us know how polluted some of our cities are. So if one were to ask what parts of your city are more polluted than others, so it's a very difficult question to answer right off the bat. But if you were able to get these pollution maps, then you might be able to say at certain times of the day, certain parts of the city are more polluted in terms of, I'm talking about air pollution, and other parts of time there is this pollution change and so on, shift and all that. Is it possible to get enough data to come up with ideas like this so that you can do smart city planning? Is another very interesting question that one could answer. In this, what we had done, and I have not put the slides for those, but interestingly what we had done was we had come up with these autometers where you could add the sensors and then you could get data about light, heat, moisture, pollution and so on, and then we showed how you could use this data in various types of very interesting data analytics which needs several different data analytic solutions and so on. So here from data which is just one type, if you were able to increase it and then increase the variety of data that you get, you could do a lot more in terms of analytics that benefits society. So this is the third example that I wanted to show. This session I am going to close with the fourth example, which is a real engineering example. This again we did with an industry. I just want to show you how real industrial data we look at analytics, what are the choices we made, and then how one gets a complete solution using these notions of data analytics. So before the last case study again, I am going to give a 2-minute break, and if any of you have any question from the beginning till now, feel free to write or raise hands and then I will be happy to answer. Since no questions, I am going to go to the last case study. So I am going to assume either, I don't know, when I teach here at IIT, when there are no questions, I tell people there are 3 possibilities. One is you have understood everything, which is very unlikely, but still a possibility. You have understood nothing, which is also unlikely. Third possibility is you are very shy. So I am going to assume that that's a third possibility. And I am going to continue with the last example, which is another engineering example that we have used data analytics to solve. So let me give you a background of how we came across this problem. All of you would know what a foundry is. A foundry is a place where you make parts, and these parts are made by pouring metal into some mold which holds the desired shape that you want the part to take. For example, many of your parts in your car are made through these foundry operations. Now, the molds could be made from several materials, and in many cases the molds are made from sand, and these are called sand foundries. And when these are fresh sand, these are also called green sand foundries. Now, typically when a foundry operates, these molds are made and parts are made from these molds, and there is a term called rejection which is very important from a foundry operation. Basically what rejections mean is the following. Supposing you were to make, let's say, 100 parts, and you do an assembly line of 100 parts, and once these parts are made, there is an inspection at the end of the line, and if 95 parts succeed in that inspection, then you are going to throw away the remaining 5 parts, and this is what is called rejection. So in this case that I just outlined, I have 5% rejection in my parts. Now this rejection is a very important thing to reduce simply because of the following. When you make 100 parts, if you know that only 95 parts are going to pass muster, and if you have told your customer that you are going to make 100 parts, then what you are likely to do is you would make maybe 106 parts even when you want to make only 100. So first you are going to overproduce, and when you do that, obviously because of your rejection, 6 of them might be thrown out, the remaining 100 will go to the customer, but the 6 of them have been made using energy. So you have lost the energy that you have put in to make these 6 parts, and also you cannot throw these parts away because the metal is expensive. So what you are going to do is you are going to reprocess them. So you will put them back into the foundry operation. So again you are going to use energy to melt them and all that. So there are many ways in which you are going to lose money. Number one, you are going to use more energy, you are going to make more than what is required, and so on. So if you reduce this rejection, you are going to have much better profit. Now it's interesting that if you look at statistics, lots of Indian foundries, the rejection levels are anywhere between 3 to 10%, whereas many of the foundries in the West operate with much less rejection. So one of our interests in this data analytics project was to really improve the efficiency of foundries in India. So the question that we asked was, could you use predictive models that somehow relate the property of the sand that is used to make these molds to the rejection type. So can we say if I have certain properties, then the projected or expected rejection ratio is the following. What I am going to do is I am going to kind of tie all of these things that I talked about in terms of data cleaning and the puzzle, jigsaw puzzle that I talked about at the beginning to this case study. The very first thing we did was we got data from lots of foundries, and unlike data that you get from simulation experiments, from very controlled experiments, this data from foundry is really dirty. We mean dirty in the sense that these data can have lots of outliers. Sometimes you can actually see that the data is not even true data because someone was not was lazy, that they didn't want to go to the field and get the data, they simply filled in numbers and so on. So as I mentioned in the jigsaw puzzle, the very first step that we really did was to look at how to clean this data. So we came up with various pre-processing rules that could be used to clean the data. This is always one of the first steps in any data analytics projects that you might want to undertake. And as I mentioned before, this is the part where you have lots of domain knowledge that you need to bring in when you clean data. So for example, there are certain bounds that we came up with, and then if you had data outside the bound, then we said these are not real data, so these are outliers, they need to be removed. So there are several algorithms that we have developed. One of the algorithms predicts the percentage of defective castings that you are likely to get as a function of SAN parameters. So if you tell me what the SAN parameter values are for this foundry at this situation, I will tell you what is the likely rejection that you will have. As an outcome of this model, you could also suggest what the SAN property should be to reduce this rejection. So that is another algorithm that we came up with. Another algorithm is, you might ask, okay, I am operating my foundry at a particular SAN parameter value and I am getting a certain rejection. You might say, look, can you tell me around the value in which I am operating, are there other values that I can use where the rejection is lower? So in other words, in a multi-dimensional space, is it possible for me to find a neighborhood of data points that I have seen before? And once I get a neighborhood of data points that I have seen before, then I can use this information to improve my process operation. So that is another question that you could answer. Another algorithm we developed was, how well are you controlling all the parameters in your process? So is there a notion of I have very good control over my process to very poor control over my process? Is there some way to find this out? So we developed algorithms for questions such as this. So going into little more details, again tying up with what we saw in the first jigsaw puzzle, there are techniques that are already available out there, but when you look at these problems, you will always have to tweak these techniques a little bit, and some of the tweaks that you make also depends on the domain knowledge that you are using. The very first thing that we did to predict the rejection based on the input SAN parameters was to build a single linear model for the whole data. So you take a foundry data, and just like the cattle hemoglobin level that we described, where the input had several variables and the output had hemoglobin, here the input variables are all the SAN properties and the output variable is the rejection percentage. So we took all the data from a foundry, for example, and then tried to fit a linear model between the SAN parameters and the rejection rate, and we found that the models were usually poor. In this case, just like what we did in the cattle case, you could have gone for nonlinear models to predict this, but one of the insights from this process was that there might be regions where there is a type of operation that is occurring. So it might be that there is a linear model that works in a certain region and another linear model that might work in another region. So that was a kind of a domain specific thing. So what we did was we came up with a clustering algorithm, which I will teach in the third session of this course, the last 2 hours, to give you an idea of how clustering is done. So what we did was we took this data and built clustering. So for example, if you have the data and then say there are 3 clusters, then what we would do is we would build a linear model for each one of these clusters. Now you notice that clustering exists, the idea of linear models exists. Here we are slightly tweaking and putting them together to build a model where clustering and linear modeling is used. So for example, if you have data like this, the clustering algorithm will figure out that there are 3 clusters, there is a cluster here, there is a cluster here, and there is a cluster here, and then it will pick out data only from this cluster, and this cluster, and for each of these clusters it will build a linear model. Now, so this is the model that is built. So you might ask, once you build the model, if I give you new data, how will you predict the value for that data? So the way we do it is the following. Supposing you have a data here, so this data is very close to this cluster, so you should use this model to predict what will be the output for this data point. So let's take a data point here. So if you have one data point here, Okay. So if you have a data point here, then this data point is very close to this cluster. So maybe you can use this model for this data point, but it's really not in this cluster. So what we do is we find a weighting. So for example, for this data point, to predict the output, I could use either model 1 from this cluster, or model 2 from this cluster, or model 3 from this cluster. So the way the prediction is done is, since this data point is very close to this cluster center, whatever is the prediction, we weight it more than this prediction than this prediction. So in other words, for each new data point, we try to find out how close it is to each of these clusters, and if it's very close, then the prediction corresponding to that model is weighted more than the other models, and so on. So you look at this equation here, where the rejection prediction is prediction from model 1, model 2 and model 3, but there are also these weighting factors that go with this. So these weighting factors basically say how close that model is to that particular cluster center. So if this data point is actually inside here, that basically means it is in this model region. So this weightage will be lot more than these two. So it will basically use that. So again, the key point that I want to make here is clustering exists, models, linear models exist, but when you combine them together and want to predict these things, these are tweaks to the algorithms that you do, and then kind of make them specialized for the application that you are interested in. So we actually built a complete software based on this, where if you give the values of the sand properties, various types of rejections and the percentage of rejection likely will be predicted. In this case, it tells you different types of rejection: broken mold rejection, erosion scab rejection, and so on. You can predict, and it will also give you a confidence of this prediction. The second algorithm that I talked about, which was neighborhood locator. So here, if you give me a value of the sand properties, what we call as a given input vector, basically the idea is, okay, if I am operating here, if you look at points around this point, can you get some sense of how well I have done, right? So in other words, I don't want any model and so on. I give you a data point, you tell me traditionally have I operated around this data point is one question, and if I operated around this data point, how well have I done? Okay, why would someone be interested in this information? I would be interested in this information because if I know that all the neighborhood points I have done poorly, then I should quickly get out of that region, right? But if there are points which are good, then I know that, okay, I can be here, but I have to kind of maneuver around to get the best performance. So that is what we are interested in. So here the algorithm, basically if you give me a data point, it will, and a value region of interest, then it will use a Euclidean distance to figure out all the data points which are within the region of interest. And once it figures out these data points, it will look at all the rejection values of those data points and then characterize the region by a mean and variance. That will give you, on an average, if you stay in this region, how well are you likely to do, and how much variability will be there in your operation is something that you can find out. Now again, notice these are specific questions that one asks in a data analytics algorithm and one tries to answer. So this is again in the software how this looks. So the math, and also finally how it looks in terms of a final product. Now the third and very interesting question that you can ask is the following. Supposing I am operating at some point, and let's say the rejection is 5% or 6% or 7%, and I am not happy with the operation, right? So I want to improve my operation. This is not what I want. I want to go to 3%, I want to go to 2% rejection and so on. So one natural question to ask is, there are so many parameters in the sand which we are claiming have an effect on the rejection. So I might be interested in asking the following question, which is, okay, there are about 13 properties that you are saying are all going to affect my rejection, but I cannot change all the 13 all at one time, right? It is effort to change the values of these properties. So I might be interested in finding out that one property when I change, which will have the highest impact on the rejection. So as an example, we see this in our lives all the time. Supposing you are studying for your exams or you are conducting your life in a certain way, and there are certain objectives you have, you want to have so much fun, you want to do so well in your exams and so on. Now if you are consistently not doing well in your exams, and there are, let's say, 5-6 habits that you have, so you might ask the question, which is the habit that I should change first so that I do much better. Obviously in many of these cases the first habit you should change is you should start studying, but for people who are already studying, is there something else that they can do? What is the thing that would have the biggest influence in terms of their performance is a question that you can ask. So the same question you can ask in this, which is to say, if I am operating at a particular point of these 13 properties, which is the property which is really leading me to this poor performance? And if I find that out, then I will devise a strategy which will help me improve my performance by changing that variable. So this is another thing that we did. Here what we do is the following. Based on our prior analysis, let's say if you have done clustering, and then let's say there are these 3 clusters, and I have good clusters and bad clusters. Good clusters are ones where the average rejection is lower, and bad clusters are the ones where the average rejection is higher. Now you might ask a question as to, if I am here near a bad cluster, how do I get to a good cluster? What is the fastest way in which I should get to a good cluster? So in which direction should I go so that I get to a good cluster faster, is a question that you might ask. So that is what this high influence algorithm figures out. So you kind of look at this and then say, if you make changes in this variable, this is what is going to give you the maximum bang for the buck. In other words, minor changes in this will give you major improvement in your productivity. So how do you figure that out mathematically? We came up with algorithms which will do it, which we call high influence. Again, this shows this. So for example, in this plot, in this screenshot, this says these are the 3 important variables, and it tells you whether you should increase or decrease and so on. So it gives you in order of importance what is the variable that is having the most effect, next effect and so on, and whether you should increase or decrease. So this will give you a feel. So this is a real data analytics solution which is being deployed in now about 10 foundries in India, and this is also being benchmarked in foundries abroad and so on. So this gives you an idea of how, from theory, which you are going to see from next class, when all of this is put together, what is the final goal of all that I am learning? So these are the kinds of applications that you can use this for. And in this class, I picked out there are many applications, but I picked out a wide variety of applications that would appeal to most of you, one or the other. The first one was medical imaging. The second one was a financial case study. The third one was really a social example where you could actually look at big data and data analytics to improve society and the way we live and so on. And the fourth example is an engineering example where there is a clear focus on productivity and improving performance. Just wanted to summarize so that you remember at least the steps that one goes through when one does data analytics, which I go back to the jigsaw puzzle. So we talked about certain concepts. How does that flow into the case study that we just saw now? So in terms of a problem definition, I said there are many things. You really need to figure out what is your final goal, right? So that is the question that you have to do. So when we started this project, there was tremendous amount of SAN parameter data. Want a solution that will reduce SAN related rejections, which was what we wanted. But to answer this question, there were several sub questions that we needed to focus on. For example, one question is, there is only data that we are looking at where the rejections we assume are due to the mold which is made with SAN. But the metal could also have problems. So should we also look at metal related rejections or not? And as we went through this presentation, we talked about once the linear model didn't do well, we could have done the kernel nonlinear model that we talked about in the cattle case study, could we have used the same thing, or the one we finally went for, which is clustering, which one is better. So all of these now in hindsight, everything looks clean and clear, but when you start the project, whatever data analytics project that you will do, the same kinds of questions will come, and then one has to be careful and smart to pick the correct approach and correct data and so on. So in terms of this problem, remember we threw out some pieces in the jigsaw puzzle. Similarly, we said we threw out all metal data. We said at the first cut, let's not worry about both and complicate matters too much. Let's remove metal related rejections. We will focus only on sand related rejections. And in terms of method decisions, because we had some intuition from the domain, we said we will only use clustering, not the kernel. And ultimately, if you notice those clusters and so on, where using high influence parameters, we are trying to go from good regions to bad regions. Finally, when we deployed this solution in real industries, we felt and we figured out that the improvements that are occurring is because of this notion of slowly moving from poor performing regions to good performing regions, by basically making changes and then seeing the effect of these changes, evaluating them with a model to suggest further changes and so on. Data cleaning, I said, is an important aspect of this approach. Again, that was a third step in your jigsaw puzzle. Here there is a heavy reliance on domain knowledge. So we had to clean quite a bit of data and use good algorithms based on domain knowledge for that. And there are also method decisions which we took in terms of using clustering based linear regression. So because of that, we had to come up with newer definitions for high influence algorithms and so high influence parameters and so on. So those are the method tweaks that we did. So just to summarize, we talked about finding out what problem you want to solve. In this case, it was reducing rejection by manipulating sand parameters. Number two, choose the correct data and correct methods. Here we chose only sand parameter related data and we use clustering as a method. Third, we said you have to clean the data and the methods. We came up with tweaks for the methods and we used domain knowledge to clean the data. And once we did all of this, we had a solution which was deployable and which has shown to have promise. One last thing is, in all of this data analytics, the next big question is really, while at the beginning of the lecture I said everything was model a while back, now everything is data, but we come a full circle and then say now there is a lot of data, but there is also some domain knowledge that is there in any one of these problems. How does one use this domain knowledge with data analytic algorithms which are purely working based on data? That is the next level of question that people are interested in answering, and we are also interested in answering questions like that. But that is at a higher level of analytics algorithms that one uses these kinds of notions. So I'm going to stop here and feel free to send questions. There must be other means of sending questions if you have. So I hope this first 2 hours gave you an idea of what data analytics means, why people are excited about data analytics, what are the fundamental components of data analytics, and how all of these come together in real problems, in solving real world problems. If I have been able to impress upon you these aspects of data analytics, that's what I was hoping for this first 2 hours. In the next 2 hours, what I'm going to do is I'm going to give you the fundamentals that you need and why you need them for data analytics. That will be a bit of linear algebra and bit of statistics and optimization, and I'll tell you why these are all the important aspects that you need to understand very well for data analytics. However, in 2 hours I've tried to crystallize as much as I can in terms of the most important details in these, which we will see in the next 2 hours. And the last 2 hours, the first part, we will teach you 2 algorithms to get a feel for how all of these things that you learn in linear algebra comes together in terms of algorithms, and we will introduce you to a case study which you can actually solve for credit for this course. Okay, so I will see you guys again next week.